9, 10. Every time you 10 oscillations, I think you caught on to that. And I don't know when you stop the time. So what times did you get?
19.82.
19.78.
19.85.
There's a nice grouping there. So 4, 7 is 11, divided by 3, so 19. So I'm getting 19.813 repeating? No, 6.
Yeah.
Okay. All right, that's for 10 oscillations, so we have a period of 1.9816 repeating is equal to 2 pi square root of 1.05 over little g. And we get 9.798 exactly. It's that good. Now, what actually do we get?
G under the square root.
G is under the square root. So you probably divide by 2 pi, square it, and then manipulate it a little bit further. Patrick, that was so quizzical, look.
Well, I got 0.1 something, which is obviously wrong.
I got that too.
So I got 1.9816 repeating over 2 pi. Squared is going to be 1.05 over g. This is some number less than 1. So g equals 1.05 divided by that 1.9816 repeating over 2 pi squared. What did you do?
What's our value again?
1.05? I'm not quite.
the
1.9, well, 19.816 repeating was for 10 oscillations, so the period of one of them is 1.9816 repeating.
I got 10.555 that time. Well, then 7 is not repeating.
Oh.
So 5.6 or 5.55, 5.56 or 5.557.
5557, all right. You get the same thing?
Yes.
Yeah, we're further up than I was expecting. Meters per second squared.
Earlier I ended up with 9.908 somewhere in the calculation, but I don't think that was G. That was some other.
Okay. I'm noticing now as I'm looking at this, that the pivot point's actually here. At this point, I don't know what it was initially. I didn't pull it back that far, so I'm wondering if that messed it up. Recognize the power of this. Galileo realized this when he was in, the story is he was in church watching one of the chandeliers rocking back and forth. Came up with the inspiration. And if I set the string to a specific length, and I know G, I can now do timing. So I think if L is about 25 centimeters, then the period is a second, which means, well, I got a quarter of a second from here to here, another quarter of a second, another quarter of a second, another quarter of a second. I have a way of timing it, at least with an accuracy of a quarter of a second. And this is a major breakthrough in terms of timing. Questions to hear? All right, why don't we take a break? We'll come back and we'll do more fun with ideals. Now we'll bring a little reality into it.
It's kind of funny that some.
All right, so I have a string here. If you're purists, I have a representation of a string here. And I'm going to pluck it. Picture it to be a guitar string if you want, but I have a string and I'm going to pluck it. And when I pull on it, I get some sort of partial wave there. And when I pull on it, it's going to propagate down. So this would be potentially at time is equal to 0. This is before time is 0. That's at time is 0. And then at some other time, it's now here. And then here, and so on. So if I was looking at the position of a spot right here, well, it's going to be different than it is in other positions as well as in time. So I'm now dealing with two different aspects of the wave, as we alluded to earlier. And some amplitude times. So I'm just going to come up with a simple formula here to describe the motion, or describe the bump. So time is equal to 0. We'll just go ahead and establish that as x is equal to 0. So when x is equal to 0, y value is the amplitude. It's going to propagate down, and so I need to somehow deal with the fact that this wave is traveling at some speed v. And as we talked about before, what happens is that if I want to shift it to the right, I need to subtract whatever amount that is. And so if I need to describe this with respect to time, some amplitude times 1 over x minus vt squared plus 1. Just like any type of transformation, if I have some function f of x plus minus phi, or some other letter, this minus z is basically going to take whatever the function looks like and shift it. That's not a function. Whatever the function looks like and shift it to the right some distance z. So if that's f of x, that's f of x minus z. So the distance that it will shift is the however fast it's traveling times time. Well, if I'm dealing with harmonic motion, I have something oscillating back and forth. So I've got a battle rope and I'm doing this to it. I'm sending waves down. And if I wanted to describe that motion, well, one, I'm going up and down, not just a single pluck. There's. I have y is equal to some amplitude times sine or cosine, whichever one you feel like. cosine for right now, times some value times x. This is not the spring constant, this is just a different value of k. And then since it's moving, propagating to the right in my head, or as time goes on, minus omega t. As we talked about before, this is the angular speed. Sorry, angular frequency. And this number right here is known as the wave number. I know that my units of this entire thing in parentheses here has to be in radians, or degrees, but radians because we're cool. And so therefore the units of k, in this particular case, of the wave number, are gonna have to be radians per meter. Just as for angular frequency, radians per second. Now, we've already established that the period is 2 pi over omega, which is 1 over the frequency. But now we have, since we have position and time involved in this equation, we can come up with an equation for the wavelength. So imagine if time stands still, and basically we're dealing with just some constant right there. Well, the wavelength is just 2 pi divided by whatever that is. I know the speed of a wave is going to be equal to, well, distance divided by time. And if I'm producing a wave up and down, if I'm producing a sine wave, well, the distance that it travels in a period, so if my time is a period, the distance it travels is just the wavelength. Because that's when I start to repeat myself. And the wavelength is 2 pi divided by k, times 1 over the period, which is omega over 2 pi. So I get the speed of the wave to be omega over k. It'd be really nice when you get to deriving the speed of light, you remember that. We'll save some time. So I'm going to take that equation, my generic, even more general equation over there, y equals some amplitude cosine of kx minus omega t. And again, not the spring constant, we just ran out of letters. And I want to do a partial derivative with respect to x. If you all dealt with partial derivatives, I got 2 nods and or 2 yeses and a no. I guess 2 nods and a shake.
I've only been through Calc 2.
Okay. Partial derivatives mechanically are much simpler. If we were doing a straight up derivative of this, we would take the derivative as normal, but we would also have to see how does omega and time and k change with x. When you're doing a partial derivative with respect to x in this case, and that's not a 2, that's a, we'll say del. Anything that's not x is considered a constant. So it doesn't matter how time changes with x, because it's not an x, therefore we don't worry about it.
So this is effectively a function of 2 variables, so it would be f of x t.
Yeah. So dy dx, well, we got the a, that doesn't change. Derivative of cosine is negative sine. And then derivative of kx minus omega t. And then derivative of this, partial derivative of this with respect to x is just k. Or negative a k sine kx minus omega t. If we do the next derivative, the derivative of that, partial derivative of that, del squared y, del x squared, what would that be?
Negative AK squared cosine of KX minus omega t.
All right. And we're probably thinking, wow, that's really cool. But that's not the end all. Now let's take this and do the partial derivative. Actually, I want to do the second derivative, but we'll start out with the first one. Del y del t. What is that equal to?
Just be 0, right? Or,
Not as long as I have a t in there.
yeah, okay, yeah. I don't.
Would it be negative a sine kx minus omega t times omega, negative omega?
Negative omega. So I end up with a omega sine kx minus omega t. And so now when I do the second partial derivative,
Negative omega squared cosine. A omega squared, I did that mistake. KX minus omega t.
all right. So it looks very similar to what I have over there. Matter of fact, there is a relationship between the two. So I got negative a k squared cosine of kx minus omega t is equal to some number. I'm just going to let q be that number for right now. Times negative a omega squared cosine kx minus omega t. And I want to figure out what q is. Well, a cancels out, the negative cancels out, cosine cancels out. What I'm left with is k squared is equal to q omega squared. Q therefore is k squared divided by omega squared. I know omega over k is the speed of the wave. So this is 1 over the speed of the wave squared. What this gives us for any type of wave that we're propagating, that can be expressed by sine or cosine, is that the second partial derivative of y with respect to x is equal to 1 over the speed squared, second partial derivative of y with respect to time. That's a bad notation there, let's see. This is known as the wave equation. And it works for any repetitive wave. So there's a number of things that we're doing right now that will apply when we get into light next semester. Doesn't totally translate over, as we will get to before the end of the day. But this is one of the book gushes over this equation. I believe it's the simplicity and the beauty of waves, something like that. Beauty and the simplicity of waves, one of those. But it is an equation that will come back. So I at least wanted to expose you to it. Now, obviously, this is just vague terms right here. We need to figure out what v is. I mean, how do you figure out the speed of a wave? besides plug it into there. Well, if I know K and omega, yeah, that's simple, but I don't necessarily know K and omega. So what we're gonna do, Newton's laws. So if I have a wave that is being propagated, I'm gonna look at a small little bit of mass here, dm. That right there is at the peak. dm has a little bit of a curve to it, so if I sort of blow that bit up, I have a tension acting here, and I have a tension acting here. I over-exaggerated the curve for the sake of writing. There's a radius of curvature here, some distance r, and because this is an incredibly tiny amount here, this is some angle d theta. Want to break this up into components, and again, badly drawn, but this angle right here, let's see if I can draw that slightly better. That was probably good enough. This angle right here, it's just half of d theta. I know, well, I've got my bits there. What's the direction of acceleration going to be? So I've got a string here, pulse comes along, we're looking at just this tiny bit at the peak. Which way will it accelerate?
Downwards.
Yes. For one thing, of symmetry, the horizontal components are going to cancel out. The only thing we're left with is the vertical components, and they're both downwards. So if I break it up into components,